This episode is with Alyssa Bulatek, an astronomy PhD student at the University of Florida. Her current focus is on star formation. Thank you for being here, and I hope you enjoy this episode. So you're at the University of Florida.
Yep, I'm up in
Do you like it there?
Gainesville. I do. I'm not from Florida, so I'm not very used to the climate, and just eternal summer all the time. Um, but I like my department and I like the public transportation in Gainesville. And it means that I don't have to be outside a lot. So yeah, I like it enough to stay here for grad school. So
Yeah. Where are you from originally?
I'm from the Midwest, so the Chicago suburbs is where I grew up, and I went to college. I did my undergrad at a small liberal arts college in St. Paul, Minnesota. Don't know why I forgot the name of the town, but yeah.
Is it what school was it? I didn't look at that.
It was McAllister College.
Okay. Yeah, I mean it's I'm sure it's very different setting from Minnesota coming to Florida. I've been to Gainesville once. I went on a visit during high school. So I played football at the University of Miami, and so I went to visit the University of Florida, like the athletic part, when I was in high school, and I spent there maybe half a day, so not very long. I didn't get to really see too much of campus or anything, but it seems like a nice place. I can't really say much past that.
Yeah, the campus is pretty cool. It's a huge campus. Like my undergrad campus was literally two blocks, two vertical blocks in the middle of St. Paul, like a residential area. And this is I don't know, we have a lake on campus, which is kind of way bigger than I'm used to. But
That's cool. Yeah, so what did you study in college, and then what's your postgrad, like your graduate degree right now?
so in undergrad, I started off as a physics major. So I was very lucky to have had an into a first year seminar course. So every student at my college had to take a first year course that it had a different topic for everybody, but they were all meant to get you oriented to college, and all of them had a writing component as well. So everyone got some writing training. I was in an astronomy themed first year course. And I was very lucky to have had AP credits from high school, so I could jump into the physics sequence at McAllister, which granted wasn't all that many classes because we're a liberal arts college and we got BAs, not BSs. But it was still physics training. So I ended up being a physics major with an astronomy emphasis, which just meant I took all the available astronomy courses, which at the time there was two, I think two. And I was also a double major with math because there was a lot of overlap between the math classes you needed for the physics degree and how much math you needed to get a math major. So I just ended up doing that as well. So I was a double major in undergrad. And then I got into an astronomy PhD program, which is where I'm at now. And on the way, I got my master's. So
Okay. When do you plan to finish your program?
that's a great question. I think I currently have funding for 5 years and the 5 years started in 2020. So ideally I would graduate May 2025, which would be 5 academic years after I started. But it's pretty typical for people in, at least in my department, I don't know if it's typical in the whole field, but for people to take 6 years, 5 or 6 years. So hopefully 2025 or 2026, depending on how much I want to get done project wise before I graduate or
Yeah,
before I get my PhD.
I'm not too sure exactly how it is for astronomy or for perhaps physics or fields such as like those. I know more so when it comes to graduate school. I was looking to go to law school, and I looked into that. I looked into MBAs, maybe PhD in psychology because I like that field, and so I'm more familiar with that. I didn't know it takes that long to like 5 years is a long time. It's a big investment.
I think for something like law school, I know law school at UF, maybe it's 2 years or 3 years because it's a little faster. And I think, I mean, I don't know, with our PhD, like the first 2 or so years or 3 years is spent getting like your master's, so like taking courses and like making sure your base knowledge is at the same level as like what they think an astronomy PhD should have. Um, and then we do like independent research projects. And I don't know if those like probably in psychology you would do like a research project and then publish that project for your thesis. But I feel like with law school, I don't actually know anything about how law school works.
Yeah, no, it's 3 years. It's 3 years, not more than three, typically,
Okay.
from what I know. And so you come in, you take your classes. It's electives pretty much all of your first year. Not your first year, sorry. After your first year, it's pretty much all electives. Your first year are like prereqs that you have to take, and then you move on to the classes you actually choose. And yeah, you graduate 3 years. You take the bar exam, and if you pass, then you can become an attorney. But I was looking into like dual JD, which is law school and PhD programs,
Mhm.
PhD for psychology, and you can complete both of them in like 5 or 6 years. And so just one for astronomy taking 5 or 6 years by itself, I think that's why I was kind of surprised.
Yeah, and looking at that, that does seem like I think we technically get 2 degrees. We're not really supposed to get a master's, but don't tell UF that. Um, yeah, it seems it does. It's a big time commitment that I think I wish that I had known at like before I went into it that like you're going to be doing essentially the same thing for 5 years, and you should know if you like it before you start it. Um, so I wish I'd known, like I wish I had been more prepared for that, but uh, I'm going to start my third year in the fall, and I think I can make it at least 3 years. And if I have to leave with just my master's, it's not the worst thing in the world.
Yeah.
Um,
But do you like it? I think that's
I
the biggest
do.
question. Okay.
Yeah. I mean, like the main thing that I'm struggling with now is like when I started grad school, I didn't really know what I wanted to do after grad school. I had a bunch of like vague ideas of like maybe I want to work at an observatory and be a telescope operator. Maybe I want to be just like a scientist as at an observatory. But I think I knew at that point that I didn't want to like go to grad school, get a postdoc, like postdoctoral position, research position, and then be an associate or like a assistant professor, associate professor, full professor, that whole deal. Um, like I didn't want to go the professor route because that's just not like how I see
Yeah.
the rest of my career. So I'm like, okay, I think I want to like teach at the college level or teach at the high school level or middle school or something. But you don't need a PhD to do that necessarily. To teach at the college level, like to lecture and stuff, you do need a PhD. But for other potential options, you don't need a PhD. Maybe you don't even need a master's. So now I'm like, should I keep going for like more opportunities or more like, just to broaden my options? And that's where I'm at now of like, yes, I will stick it out. Um, but I'm really, I think I'm more interested and more passionate about teaching than I am about just like the pure research side. The best parts of my job are where I help people like learning and stuff, and not necessarily when I'm like sitting in a room writing code that doesn't work and then writing code that does work over and over again.
Yeah, so it's similar in that sense to psychology when you say that, because the way one of the reasons I don't really want to do a graduate degree in psychology is because once you're done, I mean, you have the option of either doing research or you have the option of teaching and being a professor. And
Mhm.
I don't see too many other options beside those two. Like, where could I work? I'm not sure. Maybe be a therapist or some sort of psychiatrist, and I don't want to do that either. And
Mm.
so I really find that interesting. I think the brain is a very like in-depth thing that you can research, and I'd like learning about it. It's just I don't know where I would then apply it. I'm not sure to what point with astronomy, like that's either similar or dissimilar. Like, is it to you then can you then look up for a job? Um, like you said, I think you said an observatory, right? Like
Mhm.
what other career paths do you have once you finish your graduate degree?
I think it is relatively similar to psychology of either you do research or you teach. Um, the I'd say like probably the most common paths are if it's either like you stay in academia or you jump to industry are like the two paths that I know that people with astronomy PhDs take. And I think more and more people are jumping to industry and they're using their degrees and that they, are qualified scientists and they have experience with like research and stuff. They usually don't work necessarily in astronomy. They work in computer science or something. Um, or it's like you do research either at a university or at an observatory, but there are so few in the United States, at least. There are relatively few like national observatories that take people to like just work as researchers there. Um, and they're trying to get more and more people into the field of astronomy to like make more PhDs. But the positions within academia and at those, I guess you would still consider working in an observatory an industry job. Um, but the positions in those fields are fewer
Okay.
because there are people in them, like especially at universities. You have a lot of professors already and not many openings for professors of
Yeah.
astronomy, at least.
From what I've seen, and I don't know to what point this is actually the case, but like people in those fields and astrophysicists as well, these big time jobs at like NASA or SpaceX or Blue Origin, is that the type of things that like people in astronomy like look for? Is that the dream job you could say?
I think definitely for some people, working at
Okay.
NASA, I'd say is probably if you're an astronomer, if you're like an astronomy PhD student, you probably thought maybe I could work at NASA someday at some point in your career. Um, and there are definitely like there are astrophysicists who work at all of those companies. I but my perception is, and I don't know because I haven't looked into this, but my perception is that the grand majority of people who work there are like engineers and they have different qualifications. Like they have the more like mechanical, I don't really know what the word is, the mechanical chops versus the like if an astronomer wanted to work at NASA, they'd probably be doing like science advising for solar system missions or something of like, when we send a rover to Mars, what questions are interesting to answer about Mars or about Mars's history versus like, let's build a rover to Mars, which, both are interesting to me. But I don't necessarily have engineering experience to be able to get the other the other job.
Yeah.
And I don't know very much about SpaceX or private.
How do you yeah, no, don't worry about it. How like I think there's a lot of sometimes there's confusion or um there's not there isn't this, I guess, proper way of looking at things when it comes to the difference between maybe what like an astrophysicist does or and then what an astronomer does. And then um I was looking into different like when I was in high school and I was looking into things I could then do for my undergrad degree because I wasn't too sure. There was something called like planetary science, and there's these all these different things that have to do with space. And how are these things different? Because you said that when they go work in NASA, um, the an astronomer would focus more on you said the research aspect of it.
Yeah, I would guess that that would be the kind of job they would get hired for.
Okay. So how once, in that industry, in that professional setting, how do these from your knowledge, like how do these different jobs and different fields kind of work with each other and also how are they different?
That's a great question. I'm actually lucky enough to have friends who are in planetary science PhD programs. So well, I don't know how many there are throughout the country actually, but there's a program at UCF, like University of Central Florida, that's uh, a planetary science. It might just be like their Department of Planetary Science. Um, but planetary science typically differs from astronomy and astrophysics by like just the subjects that people focus on in the field. So planetary science tends to be more constrained to studying like objects in our own solar system. So like other planets um, or asteroids in the solar system, or probably like comets and meteorites, I think are also like, really small objects, probably also part of planetary science. Um, Earth science is even its own field. So like people who study the Earth, I would say are probably like in Earth science or Earth and atmospheric science. And I know there are a few departments around the country. Purdue, MIT both have um, like Earth and space science. Space science, I don't know what that means. Um, that's a whole nother maybe subfield. But astronomy versus astrophysics is another one that the distinction gets made a lot. I personally don't really know what the difference is. I think it depends on who's writing that distinction. Um, in at an undergraduate level, I'd say like if you get an astronomy like bachelor's versus an astrophysics bachelor's, you'd probably have more math in the astrophysics major um, versus like there's a lot of astronomy that you can do without bringing in calculus and differential equations. Not to say that an astronomy degree wouldn't have those versus astrophysics, um, but someone who might consider themselves like an astrophysicist would probably have more math in their day-to-day work. They might even like call themselves like a computational astrophysicist versus like computational astronomy sounds like more dissonant to me. Like that phrase doesn't make as much sense. But yeah, I think level of math is probably the main division between like astronomy and astrophysics. But I think functionally, if I call myself an astronomer versus an astrophysicist, I think functionally they mean the same thing. Although someone who is really part of one camp versus the other might disagree, and they might have a reason why, but I don't know.
Yeah.
I don't know what it would be.
So what do you research mainly? What are your areas of focus? And like what do you specialize in at UF? What are you looking into?
So my group that I'm a part of is like we're broadly focused on star formation. Um, I'd say astronomy up until 2016, or I'm using that as a demarcator because that's when I started paying attention. Up until recently, astronomy was totally reliant on light as its messenger for like how we see stuff from space. Like we see light from stars, we see light from like other galaxies, and that's the only way we can study like astronomy, or one of the only ways. Recently, that has opened up more because of like gravitational waves. You might have heard of that, or there's other forms of astronomy you can do, but light is the predominant like tool that we use, and light is most readily produced by stars. So people care about stars because I don't know, for a lot of reasons, but like there we can see a lot of stars in the night sky, but we don't know a whole lot about the environments in which stars are formed. Like we know the process by which stars should form in theory, but we don't know the details of like the microphysics of how like how like loose gas and dust that we can observe in space turns into like compact luminous objects. Like we see both of those things existing separately. But learning about that star formation process in a lot of different ways is what our group focuses on. We have some grad students who are focused on like the theory of star formation and considering like different ways of how like gas and dust falls onto a forming star to like make the star bigger and give it more mass. We have theorists, we have observational people. I'm focused on like observations. So I and well, the other folks in my group are also focused on this. We particularly look at the center of the Milky Way. The region is called the galactic center or the central molecular zone. It's called molecular because there's a lot of molecular gas there, which is the material out of which stars form. So the galactic center is a pretty extreme environment, which makes it like, which is why we're looking there to study star formation, because, you know, the galactic center is, I don't have a number, but millions of miles away. It's super far. There are places closer by that we could look to study forming stars, but they're, I don't want to call them overstudied because they're not really overstudied, but studying star formation in like an extreme environment is interesting because it allows us to understand a more diverse set of conditions for stars to be forming in. That might be the case more widespread in other galaxies, which are a lot more active than the Milky Way. The Milky Way should really only be forming, well, it should be forming a large number of stars a year, but it's only forming about one sun's worth of stars per year.
What do you mean by one sun's worth of stars?
So yeah, I worded that weird, but so we can talk about like the star formation rate of the Milky Way, which is just like how many stars does it form per amount of time. So we could interpret that as like the Milky Way forms one sun per year, or it forms like two stars, and when you add their masses together, you get a star that's the mass of the sun. And I don't know why we can't just count the number of stars that it's forming, and why we have to put it in terms of mass. But I think it like, so we don't know the actual number, but we can guess, we can make an estimate about like how much mass it's forming per year. But effectively, it just means we're only forming a sun per year.
Okay. So all the stars that are being formed in the Milky Way are a lot smaller in mass than the sun, from our that we can see every day.
I think I don't know like what the right interpretation is of that. I think like on average, that is true. Either you have a lot of smaller stars forming, or you just have larger stars forming really slowly. So you can form like a 20 solar mass star in the Milky Way, but it just takes a really long time to form.
I understand. So in a year, it's like how much added mass is seen in that specific star.
Right. Or yeah, like how much mass goes from like, I don't know. I have a visual on my calendar, but it's not a particularly good galaxy to look at. How much mass goes from like the loose gas and dust that we can see in those beautiful pictures of like nebulae, how much of that gets turned into a star, like that we can see as a point in the sky.
Okay. At what point does you said like the molecules, they I guess as they come into the star and the star is forming, I'm guessing they compact together, right?
Mm-hmm.
And so at what point does a specific star stop growing?
Oh, that's like an active question of research that folks are actually working on right now, or one person in the group is working on right now. I think the process of infall of material onto a star is typically called accretion, but I'm not going to use that word because it's complicated. I'm just going to say like infall. if you picture like a cloud of gas collapsing because it's gravitationally associated, all the molecules in it are gravitationally associated with each other, and they're pulling the molecules towards each other, until suddenly it becomes so compact, the infall turns into like a runaway process, and you get something very compact, and then it's dense enough to turn into a star. If you have like a huge cloud, which is sort of a more accurate picture, multiple stars are forming within the cloud. The individual like pockets of gas around the forming stars will be depleted eventually in all of the regions. So like one star that has some amount of gas around it will pull all the gas around it towards it, and then it will run out of gas to pull onto it. That, I think that's a useful picture to think about like when a star would stop. That's one theory of how star formation works. So like you have some complicated cluster, you have individual forming protostars with their larger gas reservoir, and they each take their part of the gas, the molecular gas, until the gas is gone, or until individual stars start forming and then their radiation blows some of the gas away. But I think the most useful theory that I know of is a star stops accreting either when it has the ability to, like when it turns into a star is when at the core, the like the most predominant element in the universe is hydrogen. And at the center of a star, the core chemical reaction you have is, or nuclear reaction, I guess, is hydrogen fusing with another hydrogen atom to turn into helium. If a star can start doing that, then it can stop accreting just by the fact that like if it only has a little bit of gas around it, it's gonna blow away the rest of the gas, unless the gas is infalling really quickly, in which case it can still keep accreting even after it has almost turned into a star.
So any additional molecules that are then like taken in by the star, at that point they're secreted by the gas that like comes out.
Yeah, so either that process lasts like a really long time, and so you can accrete more and more material, and then the star gets really, really big, or for lower mass stars, the like turn on is enough to just blow away the rest of the gas, and then the accretion process stops, and it doesn't, the star doesn't get any bigger once that fusion process begins.
And so when the fusion process begins is when it stops growing.
Yes, I think so.
Okay.
It's a little bit fuzzy, but like we call a star, like we say that the object turns from like a protostar into a star when that fusion process starts. And I think probably we wouldn't say that stars that have hit the main sequence that have started that fusion process accrete anymore, but you can still have like outflows and radiation pressure from protostars, things that haven't started fusing hydrogen and helium. So you can still get that material blown away.
So
and you can stop accretion.
What exactly, I'm not too sure as to what like exactly the fusion process like encompasses and what it is.
So that's physics. And I
Okay.
haven't thought about it for a hot minute, but if you get, it's a lot easier to think about nuclear processes when I think about like fission processes that happen in like a nuclear reactor, where
Okay,
like
so you mean fusion as in like two particles colliding into each other and fusing.
Exactly, yeah.
Oh, okay.
Yeah.
I thought there was like an astronomy term to it.
No, you're actually exactly
Okay.
right. That's exactly how it works. Yeah, it's nuclear fusion, like the opposite of nuclear fission. Yeah.
Okay. So once the star stops growing, within the star, do these particles start fusing, or how like what's the process there?
Yeah, that's exactly it.
Okay.
My favorite part of of astronomy is actually like the stellar evolution process. So the type of fusion that occurs within a star actually determines like what the star, or I guess it tells you what the, at what point the star is in its life cycle. So a useful diagram that we use in astronomy is called the Hertzsprung-Russell diagram. I guess if people are interested in seeing it, they can look up the picture of it. But essentially it plots how bright the star is versus how hot the star is. And all stars that are fusing hydrogen into helium in their core are on this one curve on the Hertzsprung-Russell or HR diagram. And as the star shifts, or as the star moves throughout its lifetime, it moves off of that curve and it starts fusing different elements in its core. So the fusion process begins on the main sequence with fusing hydrogen into helium. But once the star leaves the main sequence, it has like a bunch of other elemental fusion processes that can happen depending on the mass of the star. For more massive stars, which I think is actually the more interesting case, you can get helium fusion. So that's like helium atoms fusing together. I should have reviewed this because it gets, the specifics get difficult. But there's this thing where you can fuse together helium in multiple ways to form carbon, nitrogen, and oxygen, just all through nuclear fusion. And every element up until iron on the periodic table, you can actually form in the cores of really massive stars. It's so dense, like the stars are so big and there's so much material pushing down on that central core that like those fusion processes happen naturally. So you can form all the elements up till iron. I don't remember the atomic number of iron, but like maybe it's like 20 or 30 elements or 40, I don't know. But everything past iron, not everything past iron, but a lot of the elements past iron are formed when really massive stars die and they essentially explode. And then you get more fusion processes in the process of that explosion, really, really dense areas forming like copper and like weird elements that you would not think are formed, but like gold, silver, all that's formed in supernova explosions of massive stars. Yeah, so the sun right now, if the sun were out, you would be able to tell, well, you wouldn't be able to tell necessarily that it has fusion. But that fusion process of hydrogen, two hydrogens into helium, that fusion process creates a lot of energy, which is why a star is bright, is why it shines. So it's like what gives the sun its power. If only we could make a fusion nuclear reactor, we could harness the great amount of power that is generated by nuclear fusion. But alas, you need to like literally be at the center of the sun to have fusion. It needs to be so dense. So
Yeah, I find it interesting that, when I guess I feel like there has to be some sort of purpose behind why this fusion process happens. Do you know anything about like why this process is constantly going in a star? Like, does it achieve something specific?
So I think the physical like statuses that need to be achieved are you need a really high density of material so that these particles, these hydrogen atoms are bumping into each other a lot. Because I would need to brush up on my nuclear physics to be super sure about this, but I think in order for two particles to fuse, they have to overcome some kind of nuclear force. Possibly it has a name, either the strong force or the weak force, or it's just the electrostatic force between two commonly charged particles. If you have a really high density of material and you have particles bumping into each other a lot, which would also require that you have a really high temperature, then you can get just those like random chance collisions that result in a fusion of the two atoms into one larger atom. So I think that what triggers that process is the collapse of a cloud into a more dense object. And then at the center of that cloud, you achieve the high density and the high temperature that you need to ignite fusion. So I think that's what starts it. And then if it runs out of fuel, if it runs out of protons or hydrogen atoms to collide, that's what would end the process. So you need the hydrogen, high temperatures, high densities.
So when this fusion takes place, what implications does it have for everything around it? Like why is there I guess my question is there a purpose behind it as to whether the effects it has to everything around it then, I don't know, I'm gonna probably make something up, but like, does it help then the development of planets in that same system, or does it, I don't know, does it do something? Why does it start this fusion process? I'm not sure if there is an answer.
That's a good question. I think fusion at the center of a star is relatively disconnected from the rest of the material in a solar system. I think it affects the rest of a solar system in that it, like, once nuclear fusion starts, the rest of the protostar gets luminous and warm. And as planets are forming in the system, planets form for the same reason that a star forms. There's just like some part of the material around the forming star that's slightly denser, and then that pulls more material onto it, and it grows and grows and grows until it turns into a planet. Pardon me. But yeah, I think I guess it would affect it in the way of, like, if you have a really small star that is a lot less luminous, that would affect the habitable zone of the resulting, like, planetary system. Versus if you have like a really large star, very like massive hot star, the habitable zone would be, you'd have to be further away in order to like live in a system like that. So
Yeah, that's like excluding everything that the planet would have to make it habitable in the first place.
exactly right. Yeah, it would just be like, it would affect the distance at which you could survive, but yeah, you'd have to have a planet there that was actually habitable. So
Yeah,
exactly.
Okay, that's interesting. And so once you said it's called the protostar, right? So once the protostar starts having the fusion process, then it turns into a star. And once it turns into a star, I suppose the decay process starts as soon as it turns into a star, right? I'm guessing.
Yeah, I think the main like, yeah, so a star has the most fuel as it will ever have at the beginning of its life, and as it starts fusing hydrogen and helium, it runs out of hydrogen, and then it'll eventually become hydrogen depleted, or at least the hydrogen won't be in the core anymore. I'm sure there is nuclear decay, like beta decay. I know is a process that exists within stars. But really the main thing to consider when considering like how a star evolves is like what material is at the center of the star, and does the center of the star have a high enough temperature and a high enough density to fuse those atoms together into another future product.
Decay is probably not the best way to put it. Like, I guess what I mean is, like, as soon as it starts, once it becomes a star, it starts the process of dying.
Exactly.
I guess that's what I meant.
Yeah, no, that is exactly how it's a right way to think about it.
And so how does this process take place? Like, how does it start to lose fuel to then eventually explode and die?
So for I'll again take the case of massive stars because they can go through more steps. Um, so with massive stars, you have enough pressure on because there's so much material that makes them up, that once the core runs out of hydrogen, there's enough pressure to do that helium fusion. And then there's enough pressure to do fusion of heavier elements, heavier and heavier. But there's something about iron. Iron just has too high of an energy that you can't fuse two iron atoms together to make something heavier. But really, it's just like the core keeps getting more and more dense, or like it always was dense enough to do this fusion. And another interesting thing about massive stars is that they live and die extremely quickly compared to like low mass stars. So maybe massive stars only live for on the order of like 1,000,000 years or less or more, but the sun will live for many, many more years than that, orders of magnitude more than that. So the more massive the star is, the more wild types of fusion it can do in its core, but also hydrogen fusion is done so quickly in a massive star. It leaves the main sequence. If it was born at the same time as like a very low mass star, it leaves the main sequence probably before the low mass star is even done being formed. And that means that like by the end of a massive star's life, it only fuses the last like 3 elements that it can fuse. It could fuse iron for as little amount of time as like a day. So it like achieves the ability to fuse iron, and then a day later it explodes. Like a human time scale, which is really weird to think about in astronomy. But yeah, it's just like
Okay,
different types of fusion because it's more and more dense.
right. And by the process of fusing different elements together, is that how it loses fuel? Is that like how it eventually dies?
I think so.
Okay.
Because like, so the star starts off with some amount of hydrogen, and then it makes that hydrogen into helium, and the helium becomes the new fuel. But of course, it takes 2 hydrogens to make a helium. So you're limited to the same amount of material that you started with in your big cloud. So by the time you get to, fusing iron in the core, all the rest of the material in the star is these other elements, but they can't fuse. So they're like dead fuel in a fuel rod. I guess you could consider that like spent nuclear fuel. It's a little different because nuclear reactors don't work the same way. But yeah, so it's like if the material is not, if it gets pushed out, which is also like a problem in forming stars, if you like form material, it can be pushed out via just like that release of energy that happens when you fuse things. And yeah, so that's the process by which you lose viable fuel, I guess.
Okay. And at what point does it surpass like the tipping point to where it then explodes? Is there like a tipping point, or does it? I'm not sure exactly how it works.
There definitely is. I'm very unfamiliar with like,
Okay.
I know a lot about like the process by which like the gas moves before it even turns into a star. But thinking about like how do stars die? There is a mass. No, I don't think that's it. I know that the element like turnover is iron, but I can't remember why a star actually explodes. It's definitely an interesting reason, but something runaway something or other.
So once,
um,
if it's okay, don't worry about it. But if so, once iron is like present in the core of the star, then it is, I guess, safe to assume that it's nearing its endpoint.
yes,
Okay.
definitely. I think well, maybe iron can exist in the star because it was part of the like cloud, like that the star formed from. Because these are stars, this isn't like the first generation of stars that has ever existed. The ones that we observe right now, at least, we're in like the third generation of stars. That means we've already had stars forming, blowing up, and releasing the material into the interstellar medium, is what we call just like all the gas and dust in between stars. So there can be iron, and you can observe iron in stars that aren't massive stars about to go supernova. But if there's iron present in the core of the star, and the core is just like solid iron, it would be totally molten. It wouldn't be solid. But if a star has an iron core, which is not, I don't know that that's directly observable, but that would mean, yeah, it's about to go supernova because there's nothing else that can form, and then something happens and that blows up. But
Okay. And okay, so we kind of went through like the process of the star formation, but once it becomes a supernova, like what happens then? Like what you know, I'm sure it has some sort of implication to as to all the particles that then explode and protrude out into space.
yeah, exactly. So it depends on the mass of the star, but so I was saying like the things that are out there, predominantly stars, but you also have like black holes, neutron stars, white dwarfs. These are all different types of objects that are not stars, but they all form as the result of stellar processes. So for a star like the sun won't go supernova. It'll just turn into a big star. It'll shed some of its outer layers, and then it'll just turn into a core object made of electrons, like only electrons, I think. And like that's how it'll live its life. The rest of its life is a white dwarf, which we call like a remnant object, something that remains after the star has ended its life. For more massive stars, or for massive stars, stars above eight solar masses, those are the stars that can become supernova, that can go supernova, turn into supernovas. And the remnant objects for those massive stars are like neutron stars, black holes of different masses. And those are more extreme objects that are left behind when that massive star explodes. Typically, a star will have some kind of magnetic field associated with it as it is, spinning and accreting material onto it and also living its life. It will have a magnetic field because it has charged particles like positive and negatively charged ions. And so a neutron star is a remnant object made entirely of neutrons that is like essentially the core of that star that went supernova. And that has a really strong magnetic field. And that's the reason that it is an extreme and as dense an object as it is. And a black hole is created when you have the highest of mass stars dying and forming an incredibly dense object, so dense that its gravitational pull doesn't even allow light to escape from it. But you need massive, like the deaths of massive stars to form black holes. And then typically, like, to make black holes that are like big enough to matter, like the black hole at the center of the Milky Way, you need mergers of multiple black holes, I think, to make like larger black holes. But individual black holes are still formed from dying stars.
Yeah. Okay. This may be a complicated question, but what exactly is a black hole? You hear this. I mean, we all kind of heard a major overview of it, or a lot of people have heard like kind of what it is, but exactly what it is, like I don't know, and I don't think a lot of people do. I mean, if you can elaborate a little bit on what it is, you don't have to go into much detail, just so I can understand it a little better and I can input into, okay, now I kind of know what a black hole is.
Sure, I can definitely try. Um, I think a lot of popular media has given us an idea of what a black hole is that's totally like, what's the word I'm looking for? Like totally like just random postulation, like, oh yeah, like if you've seen Interstellar, it's like you can go inside the black hole and like see the past. Um, that's definitely a guess, but I feel like a lot of astronomy is also like wild guesses about how black holes work. I've heard the word singularity be employed, be used, I guess, when people are talking about what a black hole is. I don't know what that physically means, besides it's like a single point, like with no dimension, and that's like at the center of the black hole. I don't really know how that works. For what they always taught us in physics classes when I was in like undergrad was it is an object that's super, super dense. And if you get close to it, you have to start thinking about physics in a different way. Like physics doesn't work the same way as it works elsewhere in the universe because you're in the presence of something that's so massive. And so like something like effects of general relativity or just relativity in general, relativity, like all of relativity.
Yeah.
Like there are effects like time dilation and length contraction that come into effect there. So time dilation would mean that is something they did get right in Interstellar, of like when they were on like a super massive, I haven't seen it in years, but they were on a really massive planet and they're like, oh yeah, 1 minute here is like 7 years elsewhere. That probably happens very close to a black hole. And also, we used to talk about spaghettification, which is a legit word in physics, where if you were
That's a good
falling,
word.
isn't it great? It's quite accurate to describe what happens if you're falling towards a black hole, like Superman facing the black hole. If you looked at your own body, it would look normal, but to an outside observer, you would look like you were getting stretched out forever and ever and ever. Which is why, like in all those simulated images of black holes, you see like it's like a black circle surrounded by something and then like a disk around it. That disk of material is supposed to represent like the event horizon of the black hole, or like the last point at which light was falling into the black hole. And that light is essentially getting like stretched out forever. Now, black holes are not directly observable, besides like the recent images that have been put out of like M87 or Poway, and the galactic center, like the one at the center of the Milky Way that was like just released. But even
What do you mean by
then,
not directly observable? Sorry, do you mean
no
like by the
worries.
naked eye, or is it, what do you mean by that?
So like they're called like black holes, so they don't necessarily emit light like a star would. And if we try to look at like something that's dark in space, we can't see it because we're really reliant on light to be able to see it. So if we wanted to go image, like if we wanted to go look at a star with a telescope, if we were close enough to the star, we could do it. We could see it in perfect detail. But if we want to see a black hole, we have to observe it in some other way, either through observing the material that's falling onto it, that it is bright and lighting up, or by looking at another observational signature like gravitational waves, which is essentially that's usually from like black hole mergers. If you get black holes like orbiting around each other, they're so massive and extreme that they actually like contract and expand space around them in waves, and we can observe that.
So
gravitational
gravitational waves emit light,
I
or how do
think
we observe them if it's not light?
that's an
I
excellent question.
Yeah.
So yeah, I think it's a fundamentally different like way of observing than just with light. So the we observe this contraction and expansion of space by essentially putting two things some distance away from each other and then measuring the distance between them. Typically it's done with lasers on the ground, like on Earth. If you shine a laser down a tunnel underground, and you're able to tell like really well how long the laser light has traveled, you can measure like whether space has moved. And so that's how the detectors on Earth that have detected gravitational waves from different merger events, that's, I think, how most of them operate is they actually do it in 2 dimensions, both like perpendicular to each other. So you can measure contraction along one axis and contraction along the other axis. And you can kind of figure out where the gravitational wave originated from. But just like an ocean wave where it like compresses the water and then that compression moves along, you're just seeing like the compression of space as it moves through your detector, and it contracts and expands space.
The pictures that have been taken, because I've seen some pictures of black holes. How how are those pictures taken if there's no light to be able to, I guess, take those pictures properly, I guess?
Another good question. I think the light that we're seeing in those pictures is like material that has yet to fall into the black hole.
So like around it.
Yeah. So
Okay.
that's why they kind of look like rings, because
Mhm.
I think we're seeing the material on our side of the black hole falling in, but then we're also seeing light getting bent around the back part.
Right. There's no light in the middle.
Right, exactly. And that's like where the black hole is. So we're
Yeah.
seeing the whole object, but really what we see, the light that we see is just emission, like light emission from material that's falling in and is probably in a very extreme state. So it's able to emit light.
Okay. Does it draw? I've heard probably at some point before that a black hole kind of draws objects into it. Um, and I think you just mentioned it right now, like with all the objects going around it, or that seem to be around it like a ring. Is the actual center drawing those objects into it?
I think so. I think, yeah, especially for, I mean, you can think of it just like any other object. The fact that we're not really sure about what the geometry of a black hole is doesn't really matter, thanks to physics. Because if we know the black hole is, say, it was formed by the death of like a 30 or 40 solar mass star, and then the star dies, it sheds some amount of mass, and now we think the black hole is like 10 solar masses or something. If you know how massive it is, you know how much of an effect it has on the material around it. Just like if we know how massive the Earth is, we know what the orbit of the moon around the Earth should be. So past the immediate vicinity of the black hole where physics gets weird, you can just treat it like a star or something else where that has gravity. So like the black hole at the center of the Milky Way, which is called Sagittarius A star, it's not like drawing in material from everywhere in the rest of the galaxy. It doesn't have that strong of an effect at far distances. There is probably there is material directly infalling onto it, but that material probably has to get really close to be, shredded or like whatever extreme effects are happening at the event horizon. But yeah, outside of the immediate vicinity, you can just treat it like a star that weighs as much as it does.
Okay, but it doesn't emit any like heat or temperature, or it's just is it a specific temperature or no?
Oh, that's actually
Okay.
a really good question. I have no idea. I don't know. And I don't know. I
Okay.
mean, I know we can probably measure the material of measure the temperature of the material falling into it,
Mhm.
but I'm not sure if like a quiescent, like a black hole that stuff is not falling into, if we could just measure the temperature of that. That's an interesting research question that someone should look into, definitely.
Yeah, because I mean, I'm not sure exactly how the material that is, I guess, expelled once the star explodes. Um, I'm not sure if it's still like, does it maintain the temperature? Does it then, um, lower the temperature of all the different elements that are, expelled into space? And if they are, like, I would suppose that, um, the black hole itself, I don't know, maybe it's still, since it was, at some point a sun, maybe it would still, I guess, have some warmth to it in terms of temperature. I'm not sure. I'm just making things up.
I mean, I think that's a really good guess. It would make sense, right, for it not to change temperature if the situation hadn't changed. And I think, yeah, so that like out the material in a supernova, as it moves out into like empty space, it's going to get cooler.
Mhm.
As it expands, and like space is really good at, it's a really good insulator, so it'll just take the heat from that process and like dissipate it. But yeah, I have no idea if I would expect it to be very warm, but then my immediate association is like things that are luminous are warm, things that are not luminous are cold, but that's not always true in space. So I think
Does
you
does
could be
does space
definitely
have
right.
like would you is I'm sure it varies, depending on what part of space you are, whether you're closer to a star or further away. But is there a temperature at which space um tends to be in?
I think it definitely does vary. I would say generally very cold. Most of space is empty. Um, and if there's nothing, if there's no material, if you're like near a vacuum, there's no material to generate that temperature. There's no like vibrating molecules releasing energy. Um, the actual, uh, I don't know if this is exactly like a right interpretation of this phenomenon, but if you've ever heard of the cosmic microwave background, um, people refer to it as like the baby picture of the universe. It's essentially we used a satellite telescope and now telescopes on the ground to see as far away as we can possibly see in the universe, and to see like what is that background, like what does that furthest surface look like. And we can measure, because it's a radio telescope doing the measurements, we can measure when we see how bright it is, it's actually linked to the physical temperature of that material. And it turns out that the temperature of the cosmic microwave background is about 3 Kelvin. 0 Kelvin being absolute zero, no movement, heat death of the universe, like the coldest ever. So 3 Kelvin is very, very cold. Room temperature is about 300 Kelvin. A lot of like loose gas and dust in space is between 10 and 100 Kelvin. So like space where there's nothing, I'd say probably on the order of 5 Kelvin. Extremely cold. Of course, if you're right near a star, millions and millions of degrees Fahrenheit. Um, but yeah, like you
Okay,
said,
so
it can
that
definitely vary.
so then it makes sense then that the black hole is not hot, like I was supposing.
I mean, you never know. Like, because it used to be, because it's the remnant of this massive star, and the core of the massive star was really hot, like so that it could, fuse iron, or everything up to iron. Maybe the remnant object is really hot. I don't know. Maybe someone out there has done a like. I think it would probably have to be theory at this point of like, what do we theoretically think this temperature should be? Um, but if not, I'm sure somebody who studies black holes would definitely appreciate that suggestion of, hey, we should try to figure this out, because I'm sure there's a
Yeah,
way to estimate it.
yeah. And there's a lot that goes into I I have never really looked much into like specifically star formation. So now that you're telling me all these different things, it's very eye-opening. I think it's really cool because you don't when you look into things to do with space, you'll learn about planets, or maybe in YouTube videos, a lot of times, you'll see, oh, there's this planet certain million light years away or whatever that could possibly have life. And so you learn about that, or you learn about um I don't know, maybe comets that pass near Earth, stuff like that. But when it comes to the details and specifics of star formation, it's not as easily accessible, I think, as other aspects of astronomy and space. So I think that you shedding light on that, I think that's pretty cool. And it seems like an interesting topic to research in depth. And I'm sure there's a lot of things that you've learned and probably will continue to learn. So that's pretty cool.
Yeah, I appreciate getting the chance to talk about it because yeah, like I feel like a lot of the popular science of astronomy is like exoplanets because people are really interested in, other Earths out there. And I think that's definitely interesting. But I also think stars are pretty interesting and like how they live and die is sort of the bread and butter of astronomy, or what it has been for the past uh, century, probably. People are pretty focused on stars. Um, so I like it, and I'm really glad that I got to talk about it with you.
Yeah. Well, I mean, one last thing I want to ask you. Like our sun, and I think a lot of people, or at least I personally, I've looked into our sun, and I think we all know at some point it's gonna explode, and everything we know is gonna end. But how, as for, I think you call it solar masses, right? How big is our sun compared to other stars, and um, what's it like? At what point of its life is it right now?
That's a great question. So our sun, yeah, the fact that we made the units of mass solar masses is kind of useless to think about. Like, how massive is our sun? Well, it's one solar mass. Um, it's so other stars can range from a tenth of a solar mass, probably would be the smallest star. So like uh, those would be like a K type or M type star. Our star, oh, I shouldn't even go into the classification of stars because we messed those up. The letters don't go in order. Um, but you can have like a tenth of a solar mass, or you can have like tens of solar masses. Um, so yeah, our star is right in the middle. It's 10 to the 30 kilograms, which means nothing to me. But that's how much one solar mass is. And I think our sun is in the middle of its life. I seem to recall that being the like age estimate for the sun. Um, but the sun is like, I don't want to say a number that's wrong, but I'm going to guess it's billions of years old. And that means it will continue to survive in its current state on the main sequence for like billions of years still. Um, so I think humans probably shouldn't worry about the sun at any time in human existence, because I would be, I mean, I sure hope that society still exists by the time that the sun starts expanding. But I think that expansion will actually be a slow process.
I'm sure by
Of
then we'll be able to go somewhere else.
probably.
Yeah.
And the other thing is the Milky Way is going to collide with the nearest galaxy, Andromeda, I think before the sun would expand into a red giant and consume the Earth. So
I didn't
I
know
might
that.
I might be wrong about those timescales, but like we'll have other interesting things to think about at that point.
Yeah. And there's bigger things to worry about right now.
Right. Yeah. I think we should focus on looking down and around rather than thinking about cosmic interference in life.
Yeah. Yeah, totally.
Do you have the opportunity to take like outside of your discipline courses? Like, could you take an astronomy elective? Or
I have, so I'm graduating here soon, December. And
congrats,
I
nice.
thank you. And again, I was looking into different graduate programs, and but when I was in undergrad, instead of wanting to take electives, I wanted to take minors.
Mm,
Um,
mhm.
I just feel like they would provide me with more in-depth look at the things I was somewhat interested in. Because my major, I'm not a big fan of my major. It's business technology. It's like computer science
Mm,
within business, and so it's coding, um, cloud platform, like evolution, stuff like that. It's not that interesting, to be honest.
I see.
My minors are psychology, um, filmmaking, and business law. But
Those are
there's
all
and so
cool.
and s- yeah, and so I took those things instead of taking other electives.
Mhm.
But going into college, like one of my favorite things was space, and it still is. And I was looking at doing um, like I was looking at maybe doing or majoring in astrophysics. I was looking at maybe majoring in aerospace engineering. Um, but I wasn't that great at advanced math, and I
Mm.
figured that could maybe be a problem. And so I was like, you know what? It's just not, maybe something like astronomy, which is a little less math and like intensive. I could have probably looked into, but as for those like engineering programs, I don't know. I didn't really want to get too much into those, but yeah, that so I answered your question a little more thoroughly, but I didn't
Oh yeah.
take an astronomy elective, and just because I wanted to focus on my minors, but I still want to learn about it. And one of the reasons why I'm doing this podcast, and probably the
Mhm.
main reason, is because I get to invite people like you. I the other day I talked to a professor of history at my university, at the University of Miami,
Mhm.
and he specializes in it's in like Mexican history, and but more specifically, what he's researching right now, which I think is pretty cool. It's um, it's like this of the evolution of you of like hallucinogenic use in Mexico of like psychedelic drugs, and how the ancient cultures changed their usage when the Spanish got to Mexico. And
Whoa.
yeah, it's things you don't, read about or see every day, and you get to learn from these people because they focus on specific things. And again, like I
Mhm.
was telling you earlier, you get to see about these exoplanets, or pretty broad topics when it comes to astronomy or any other field. But when it comes to these more specific things, you don't really learn as much. And so having these people on here, um you get to learn a lot of stuff, and I like learning. And so that's probably the main reason why I'm doing the podcast. Is just so I can learn more things. When it comes to learning things that I enjoy, it's fun, because a lot of times we learn stuff in school or growing up or whatever that we don't really enjoy, and then school becomes boring, and it's just kind of this thing you got to go through. But then if you actually get to learn about things that you want to learn about, and me reaching out to people on fields that I want to learn more about, then it's something that it's actually enjoyable, and you pay attention, and you take away good things from it. So that's why I do this.
I think that's so cool. Like, I think a lot of times, especially like in graduate programs, people will lose sight of like learning is fun, learning can be fun because it turns into a 9 to 5 and a grind. Um, but I think that's so cool, especially to be able to ask like such a diverse group of people and like to just reach out to like history professors or like astronomy grad students. Like it's so cool. And like
Yeah, and
good for
like,
you for
thank you.
pursuing fun learning.
Yeah, thank you. And it's I think I want to learn about these things, but then also by putting this out there or any other conversation I have with someone else, I'm sure that just like me, there's people that want to learn about other things. I mean, you seem like a very curious person. I'm sure if you're doing this, you're intelligent, and I'm sure you're ambitious, and you want to learn things, and probably yourself and other people that are interested in that sense. I think it's always good to talk to a range of people just because, oh, maybe, I don't know, someone might be interested in anatomy. And so if I talk to a person that is a doctor and then can talk about that, and then they can listen to that
Mhm.
conversation, maybe they can learn a thing or two and they're interested in that, so they will pay attention. And
Right.
it's just, it can be tailored kind of to anyone that not tailored, but it can appeal a bunch of different people
Mhm.
because it's a different, it's different fields that people can talk about. And so it's not just for me, it's for anyone who wants to maybe learn, because at the end of the day, like I said, if you want to learn something, if you actually enjoy it, then it'll be a lot easier to pay attention to it and actually learn.
Right.
Yeah. So that's again, that's why I wanted to do this.
That's awesome. I think it's also cool that one of your minors is filmmaking. I've recently, uh, I wouldn't say I'm interested in pursuing filmmaking because I think I would have had to jump into that earlier, but I'm very interested in like the process of filmmaking and learning about that. And I just didn't realize that you could just do that in college. My college was really small. Um, but did that inspire you at all to make this podcast? And did it give you skills to do that?
Well, everything editing wise is because I've
Mm.
done movies before.
Whoa, that's awesome.
Well, like short films, not yeah.
Right, right.
I didn't
Well, I
I
mean,
didn't
still,
make
that's cool.
Interstellar, but um, like 5, 6, 10-minute movies, documentaries that I've shot and I've edited and I've done. And so, you know, all the editing software that I use, I know how to use because of that. And so
Nice.
that's just I think that's the biggest skill that I've taken away from it so far. Um, I've gotten to um I've learned how to use certain cameras, certain equipment. It's yeah, it's a lot more complicated than maybe one thinks, because when you look at a movie and you don't really know much about filmmaking process, you
Mhm.
don't pay attention to things that then you do if you do learn about it. So
Right.
one of the biggest things when I look at a movie or whatever now, um, I look at the way uh like certain scenes kind of flow because of the editing. And
Mhm.
so I don't know if you watch Stranger Things.
I have not. I watched season one, but I've been watching a lot
Okay.
of compilations lately to try to like get myself hyped up to watch it.
Yeah, so Stranger Things, very good, by the way. So
Mhm.
you should try it again if you want, if possible. But um one of the things that I really enjoyed about it was how well done the editing was. Like you'll
Mm.
have some scenes where it's, I don't know, it's taking place in the mountains and the snow in this fourth season that came out. And so it'll
Mhm.
be a scene with the mountains and the snow, and then they'll kind of move the camera up to record the sky with like the snowflakes falling, and then as the camera keeps moving up, like it'll then appear in another scene where it's maybe, I don't know, like the desert or something, but they blended the color and the transition in the editing to then go from like the
Oh,
snow to then up to the sand to then the desert, and it's another scene, and it's like seamless.
wow.
It's stuff like that. I don't remember if that was exactly the scene how it happened, but it was something like that. And
Mhm.
oh, I think it was actually with the snowflakes, and then it was some sort of explosion, and so they transitioned over to like the ashes falling, and so you have
Uh,
the different like scene. And so like these things you don't really notice when you're just watching the show without ever editing, really,
mhm.
or not for the most part. And so I've gotten to appreciate those things. I'm like, that was really cool. Like that's not easy to do, and the fact that they do it so often and so well, it's really cool. Um, but yeah, it's just you get to appreciate things a little differently. I'm sure from an astronomy perspective for you, whenever you see an article or a movie or whatever, like Interstellar, you were saying, you're able to dissect it a lot more and pay attention to certain things that if I watched that, I'd be like, oh, that's cool how he just went into that black hole and I don't know, this happened.
Yeah, exactly. Like even just you talking about that transition, I was like, yeah, I'm just like, whoa, but I don't even think about what went into it. And yeah, I think it's sort of similar in astronomy. A lot of like even with math stuff, sometimes I watched Goodwill Hunting twice on a plane a couple weeks ago, and I'm not a math expert, but there was so much like so many words that I'm like, oh, we don't really use those words like that. We don't really say like McLaurin without the word series after it. Um, but maybe math people do. But yeah, it's like it's kind of easy to tell when you've been steeped in the terminology and like you know that background.
Yeah. Yeah. So I mean, I've been, one of the things that I was looking into maybe after I graduated was film school because I liked that idea. The only problem is I think the whole um like industry for entertainment is kind of I don't think it's very it seems to be very superficial and it's just not something that I would particularly enjoy. I've heard stories about, how it's corrupt and
Mhm.
how it's this like nasty business to get into. And I don't know if I really want to look into that. So
Mhm.
there's other aspects that you have to consider as well. Um, when it
Right.
comes to something that you're interested in. Yeah.
So are you
So
thinking
I'm
about
just
like law as a
I was, but not anymore. It's boring.
gotcha.
Yeah, like
That's my perception of it too.
I was thinking about it, and then I started preparing for the LSAT, which is a law school admission test that you have to take.
Mm,
And so I was going to take it this summer, probably August or something.
mm,
Uh, but then as I prepared more and more for it, and I heard podcasts about law school and watched videos about lawyers and stuff like that. Um, I, it just I don't know. It seems like a lot of people in that field are unhappy,
mm,
and like the thing that appealed to me about it was like the debating part of it because I like that. I like preparing an argument and going
mm.
up and maybe trying to argue for my side or whatever. I like that aspect of it, but then the law itself I think is pretty boring.
Yeah.
And I'd have to be dealing with that the whole day and then just maybe, I don't know, once every couple of weeks then be in court if that's what I wanted to do. And so most of the time I'd be doing something I wouldn't like and there's really no points. I have to find something or in my head I'm telling myself that I have to find something that I really like truly enjoy. Just because when you do really enjoy something, you're willing to put in so much more time, so much more effort. And when you're willing to do that, then that's what can help you be successful. And we all want to be successful in whatever it is that we do.
Right.
And if you don't really like it, you're gonna be kind of like dragging yourself through the mud while you do it every day. And you're not gonna want to put in extra time. And that's not gonna help you excel in whatever it is you're doing. So I want to find that something. I'm not sure what it is yet though.
I'm in the exact same position of wanting to find that. Um, I hope that you find that. And
I hope that
I
you
mean,
find
that's the
that
goal,
too.
right? Thanks.
Yeah. Do you have anything in mind that you things that you want to try out? My plan, let me just
Yeah.
share this real quick and then you can tell me. My plan is I'm gonna start working this as soon as I'm graduate this December. So January I'll start working. Um probably in what my major is, which is business tech. So I'll
Mhm.
probably start doing cybersecurity, software development, some stuff like that. Just because I have to live and earn a living,
Yeah.
because if not, I'm not sure where I'm gonna get money to go on every day. But
Mhm.
yeah, so I'll probably find a job in that I somewhat find enjoyable. And a good thing is in that industry they usually tend to pay well. So at least for the
Nice.
beginning, I can save some money. And the goal is to try different things as I like work and see what I like, what I don't like, and actually try to find something that I really, really do like. That's my plan. I'm not sure if you have something in mind as for what you're gonna do or what you would like to try out.
I think that's really smart. I wish my plan involved saving money. uh, my current plan is to finish my PhD program or leave before my master's, depending on if I get bored enough. Um, and I'm interested in trying out teaching because I'm thinking that teaching is going to give me the satisfaction that I want of like, I want to help people with my job. And it's harder to do that if you just study space all day. And so maybe I'll try to start teaching at the college level because that will at least pay something. I'd also like to relocate to somewhere where we have winter because I'm really used to cold, and I think I'm losing my cold tolerance, which I don't like. So I probably won't save money, but maybe I can move to somewhere where there's not a high cost of living. And so I'll try to teach for however long I can. Or like if I hate it immediately, then uh-oh. But yeah, I guess teaching is what I'm going to try next. And if I have to give up on that because it doesn't work for some reason, then maybe I'll pivot back to the other ideas about like what kind of jobs astronomers can have. I'll see if there's any openings at like for researcher positions where I'm not coming up with my own research ideas, but I'm working on other people's at observatories. I know jobs like those exist.
Yeah, but I mean, thank you again, and thank you for your time, and that I'm sure that whoever listens to this will be able to learn a couple things, and I hope that you find your thing as well.
Thanks very much. Thanks for the chance to talk and share
Yeah,
what I
yeah.
know and get to discuss.
Thank you.